So whenever you're performing a stoichiometric calculation, including determining the mass relationship between reactants and products, calculating limiting reactants, and the percent yield, the first thing you have to do is balance the chemical reaction. Then look at all your possible mole ratios because, like we said earlier, those become your conversion factors for the problem. Calculate the molar masses of a substance if needed. Set up dimensional analysis, so set up your railroad, and then solve the calculation. Somewhere in your notes where you have a blank space or on the back page, I want you to write this mole road because this will become your roadmap for your calculation and problem solving. I'm going to either give you grams of something, so grams of A, or I will give you moles of A. And I will ask you to find moles of B, or I will ask you to find grams of B. So you will either be given grams or moles of something, and we call that something your A, and you're going to be asked to find grams or moles of something else, and that's what you want, so we call that our B. Well, if I give you grams, and you're starting with grams, you can't do anything in chemistry if it's not in moles, right? So even though in the lab we use grams to mass out our reactants, when you're doing any kind of calculation, it has to be in moles. So how do we turn grams into moles? We'll think back a couple of units ago. To turn grams into moles, you had to divide by the molar mass. How do you find the molar mass? Well, you look at your periodic table, you look at the masses, and then you add them up. So H2O, that's 2 hydrogen, which has a mass of 1, plus 1 oxygen that has a mass of 16. H2O has a molar mass of 18. I'm going to jump over to the right-hand side. If I ask for grams and you have calculated the moles, how do we turn moles into grams? Well, you multiply by the molar mass. So anytime you see a problem and you see grams in the problem, that's a key word that tells you you have to find the molar mass of whatever substance is attached to that unit. So the new part for this unit is this middle part, this moles of A to moles of B. And that's where we use those conversion factors that we wrote earlier. That's where we use our mole ratio. So to convert from moles of A to moles of B, we use our mole ratio. All right, let's take a look at a practice problem here. Calculate the number of moles of oxygen needed to produce 4.334 moles of H2O. We need a balanced equation for this, and most of the time you'll already have it, but for some reason this slide doesn't. So H2 plus O2 yields H2O. Let's put a 2 here. So 2, 1, 2. So there's my balanced equation. I'm giving you 4.334 moles of H2O. I'm asking you to find the number of moles of oxygen. So when we look at our balanced equation, even though we see 3 things in this balanced equation, we can only look at two of them at any given time. And in this case, we're comparing H2O to the O2. For now, you can pretty much ignore that hydrogen part of the equation. So all stoichiometry problems start out the same. You're going to start by writing down your given, 4.334, and it's important that you include the unit, moles of H2O. Ultimately, I'm trying to turn this into moles of oxygen. So when you're using dimensional analysis, what you want goes on the top. How do I get rid of moles of water? Well, moles of water has to go on the bottom of my conversion factor to cancel that out. And then this spot here, those 2 numbers, that's where we put in our coefficients. So there are 2 water for every 1 oxygen. There's 2 moles of water for every 1 mole of oxygen. And then at this point, you would go and multiply across the top, so 4.334 times 1 divided by 2. And we get 2.167 moles of oxygen. So just to review where my numbers came from, the 4.334, that was given to me in the problem. The 1 and the 2, that's my mole ratio, and I get those numbers from the coefficients in a balanced equation. And then this is my final unit. And then 2.167, that's my answer. Let's look at another calculation. How many moles of NH3 are produced from 3.678 moles of hydrogen? Let's get our balanced equation for this. Hydrogen plus nitrogen yields NH3. 3. So you should get 312 for your balanced equation. Let's write down our given, which is 3.678 moles of hydrogen. And I'm asking you to find moles of NH3. Start by writing down your given, 3.678 moles of hydrogen. And then to cancel moles of hydrogen, that has to go on the bottom. So there are 3 moles of hydrogen. And I'm asking you to find NH3, so 3 moles of hydrogen for every 2 moles of NH3. To solve, we multiply across the top. So 3.678 times 2 is 7.356. We divide by the bottom, divided by 3, and I get 2.452 moles of NH3 for my final answer. So where did those numbers come from? Well, the 3.678, that was my given. That was given to me in the problem. The 2 and the 3, that's my mole ratio. Hydrogen has to go on the bottom so that it can cancel out the moles of hydrogen that was given to us in the problem. Moles of NH3 is what I want, so that's the number that's on top. And then we multiplied and divided. And in this case, we didn't even really need to work with that nitrogen because in any problem, you can only work with 2 components at a time. All right, so why don't you go ahead and try this next problem on your own. Aluminum sulfide yields aluminum plus sulfur. Identify the type of reaction, write the mole ratios, and then find out how many moles of aluminum are created when 7.912 moles of sulfur are created in the reaction. All right, so hopefully you took the time to try to solve that one on your own. When you balance the equation, it was 1, 2, and 3 for your coefficients. This was a decomposition reaction. And what we found out was that if I started with 7.912 moles of sulfur that were created, I would also produce 5.27 moles of aluminum at the same time.